Have you ever wondered how raw rocky sulfide ores are transformed into pure metals? In this video, we will explore the fascinating process of smelting sulfide ores. We will examine the various chemical reactions that occur during the smelting of different sulfide ores, such as copper, lead and zinc, and provide a detailed breakdown of the entire process. Welcome to the channel. What are sulfide ores? Sulfide ores are natural mineral deposits in which metals are combined with sulfur, forming sulfide minerals. These minerals are crucial for extracting metals such as copper, lead, and zinc, among others. Sulfide minerals are compounds where sulfur acts as an anion, combined with a metal or semi-metal cation or cations. They typically form in reducing environments that have low or no oxygen content. However, sulfide minerals can become unstable and oxidize when exposed to atmospheric oxygen, leading to the release of metal ions into solutions. Sulfides represent the most important group of ore minerals, as they are responsible for concentrating a wide range of metals into mineable deposits. Examples of sulfide ores are galena, the primary ore mineral for lead; sphalerite, the primary ore mineral for zinc; chalcopyrite, a copper iron sulfide that is a major source of copper; cinnabar, the main ore mineral for mercury; argentite, a silver sulfide; molybdenite, the most important ore for molybdenum; stibnite, the main ore mineral for antimony; chalcocite, a copper sulfide, etc. Why is sulfide ore smelting necessary? Sulfide ore smelting is necessary for two main reasons. 1. Extraction of metals. Smelting is a pyrometallurgical process that uses high temperature to extract metals from ores by reducing metal oxides or sulfides into their metallic forms. 2. Separation of metals from impurities. The smelting process separates valuable metals from sulfur and other impurities present in the ore, resulting in a molten metal phase that contains the desired metal and a slag phase that contains the impurities. Let's look at the smelting process of selected sulfide minerals, copper, lead, and zinc. Non-ferrous metals such as copper, lead, and zinc are found in nature in the form of sulfide minerals. These minerals undergo beneficiation through various mineral dressing methods, such as flotation, to produce concentrates that are rich in specific metal sulfides. The sulfide concentrates are then subjected to a pretreatment process called roasting, which occurs at temperatures ranging from 500 degrees Celsius to 800 degrees Celsius. During roasting, sulfur is oxidized to sulfur dioxide, and the metal sulfides are partially or completely oxidized to their corresponding metal oxides. The degree of sulfur removal required varies depending on the metals. For lead, the sulfur is completely oxidized to lead oxide. In the case of copper, only the iron sulfide impurity is partially oxidized, while other sulfides remain intact. The hot exhaust gases produced during roasting, which contain sulfur dioxide and sulfur trioxide, are utilized in the manufacturing of sulfuric acid. Next, we will examine the stages and reaction processes that take place in the smelting process for each of these metals. Copper. Copper is primarily found in the Earth's crust as copper sulfide minerals, such as chalcopyrite and chalcocite. It also occurs in oxidized minerals, including malachite and azurite. Copper is mainly extracted from its sulfide ores. After mining, the ore is crushed and ground into a fine powder. This finely crushed ore is first concentrated using froth flotation. In this process, the ore is suspended in water with a small amount of pine oil. A blast of air is passed through the suspension. The ore particles become wetted by the oil and float to form a froth, which is then skimmed off. The unwanted material or gangue sinks to the bottom. Next, the concentrated ore is roasted in a furnace at a temperature between 500 degrees Celsius and 700 degrees Celsius in a limited supply of air. During this roasting process, iron and some sulfur are removed. The sulfur is oxidized to sulfur dioxide. Impurities such as arsenic and antimony are also removed as volatile oxides. The overall reaction in this roasting stage can be summarized as follows. Ferrous sulfide is oxidized into its oxides. The roasted ore is then mixed with coke and silicon dioxide and smelted in a furnace at around 1200 degrees Celsius in the absence of air. This process removes iron 3 oxides as iron 3 trioxosilicate fall slag. The slag can be easily removed, as it floats on top of the copper sulfides. At this stage, a matte containing approximately 60% copper has been produced. Copper matte is extracted from the molten matte through a process known as bessemerization. Here, copper sulfide is heated with a regular supply of air. The air is blown through the molten matte, converting some of the copper sulfide into copper oxide. This copper oxide then reacts with the remaining copper sulfide to produce molten copper. The resulting copper, known as blister copper, is around 98% pure. However, this purity is insufficient for industrial use. To refine blister copper, an electrolysis process is employed. Blocks of blister copper serve as anodes, while thin sheets of pure copper act as cathodes. The cathode plates are coated with graphite to facilitate copper deposition. The electrolyte used is an acidified solution of copper 2 sulfate, copper mixed with a small amount of sulfuric acid, to enhance electrical conductivity. As electric currents pass through the cell, copper ions from the anode dissolve into the acid and are subsequently deposited on the cathode. The impurities remaining in the copper anodes settle at the bottom of the tank as anode mud or sludge. The refined copper obtained through this electrolysis process is 100% pure. Lead smelting. Lead is not usually found in its pure metallic form in nature due to its reactivity. Instead, it is typically extracted from its ores like galena through processes such as roasting and smelting. Other common ores from which lead can be extracted include cerussite and anglesite. After the beneficiation process, which involves the extraction and concentration of the ores, the smelting process of lead begins. The smelting of lead ore is based on 3 principles. 1. The roasting of the ore. 2. The reduction of the roasted ore by carbon or carbon dioxide. 3. The precipitation method. The concentrated lead ore is roasted in the presence of oxygen. This process converts lead sulfide into lead oxide and sulfur dioxide gas. The roasting is necessary because the sulfur content prevents carbon from reducing the lead. Thus, the mineral must be oxidized first to create a metal oxide from galena. The reaction during roasting can be represented as: during this roasting phase, some of the lead oxide reacts with the remaining lead sulfide to form lead metal and sulfur dioxide. The lead oxide obtained from roasting is then mixed with a reducing agent, typically coke, in a blast furnace. Limestone, flux, and other additive can be included depending on the impurities present. The carbon reduces the lead oxide to molten lead according to the following reaction. This process is known as smelting. The crude lead produced through smelting contains impurities such as silver, gold, copper, and bismuth. This lead is further refined through several processes. They are: 1. Liquation. This process removes metals with lower melting points than lead. 2. Parks process. Silver and gold are separated by adding zinc, which forms an alloy with these metals, allowing them to be removed from the lead. 3. Electrolytic refining. Lead is purified by electrolysis, yielding highly pure lead. Zinc extraction. Zinc occurs in nature mainly as sphalerite, zincite, calamine, smithsonite, and franklinite. Typical zinc ores generally contain about 5 to 15% metal. Given the low concentration of zinc sulfide minerals in most zinc ores, the ore must first be concentrated before smelting. Zinc can be extracted through both pyrometallurgy and hydrometallurgy processes. For the pyrometallurgy process, after the beneficiation of the zinc ore, the concentrated zinc ore undergoes roasting. This roasting converts sulfide zinc ores into their oxide forms by exposing them to oxygen, which removes sulfur dioxide at temperatures between 700 degrees Celsius and 800 degrees Celsius. This reaction is exothermic, raising the temperature up to 1000 degrees Celsius. The zinc oxide is then reduced to metal using either thermal or electric methods. In a blast furnace, zinc oxide is reduced with coke, while a blast of hot air is introduced at the bottom of the furnace. The excess carbon reacts with the oxygen to form carbon monoxide. Higher up in the furnace, carbon monoxide reduces zinc oxide to zinc. Some carbon dioxide can directly react with carbon to produce more carbon monoxide. Additionally, some zinc oxide can directly react with carbon. Since the temperature in the furnace exceeds the boiling point of zinc, 907 degrees Celsius, the zinc vaporizes at around 1000 degrees Celsius and is carried up through the furnace by the stream of carbon dioxide and carbon monoxide. The vapor is readily cooled to 550 degrees Celsius in a molten lead bath to produce condensate zinc, which contains small amounts of cadmium. The zinc is then purified by distillation. However, this method produces only 20% of the world's zinc. The electrolysis of zinc sulfate is now the preferred method, leading to much purer zinc. The electrolytic refining process, which is a hydrometallurgy method, consists of 4 steps: leaching, purification, electrolysis, and melting and casting. After roasting, the crude zinc oxide is dissolved in dilute sulfuric acid to produce a zinc sulfate solution. After filtration and purification of the solution, zinc sulfate undergoes electrolysis using a lead, with 1% silver, as an anode, and an aluminium cathode. Oxygen is released at the anode while zinc is deposited on the cathode. The sulfuric acid is regenerated at the anode and can be reused. The zinc is periodically stripped from the cathode, melted, and cast into ingots for various applications. Electrolytically refined zinc is typically 99.995% pure. Approximately 80% of the world's zinc is produced using this process. In conclusion, the smelting of sulfide ores such as copper, lead, and zinc is not just a chemical process. It is a fundamental technique in modern metallurgy. Each step of the process, from roasting to reduction, is meticulously designed to extract pure metals from complex mineral structures, supporting a wide range of industrial applications. Understanding how these metals are produced not only enhances our appreciation for modern technology, but also highlights the importance of sustainable practices in metallurgy. If you found this video informative, please like, share, subscribe and hit the bell icon so you won't miss any of our future videos on materials science, metallurgy, and engineering. Thank you for watching, and look forward to seeing you in the next video. Goodbye.